Hello, everyone. Welcome back. We are now working on chapter 5.3, the last section 2.2 on vector analysis. Here, we're going to learn about spatial joints. Spatial joints are a way to take two layers and find features from one layer that have a specific geometric relationship with another features from another layer. You use spatial joints in variety of contexts. Here is one example where, let's say, we have this green layer of points, which are the trees. So San Francisco, city of San Francisco collects data on where the trees are. And this is a vector data of where all the trees are in San Francisco. And you have this polygons in blue, which are on the neighborhoods. And you want to count how many trees are present in each neighborhood. So counting points in Polygon. That's a classic spatial joint operation where you say, tell me how many points intersect each polygon, and I want to count of that. And spatial joints allow you to also say, give me for each tree, join it with the polygon and say, what is the neighborhood for this tree? So I want to add the attribute from the polygon layer and join it based on the spatial relationship. Or you can also do things like I have a roads layer, I have the length of roads, I want to know what's the total length of roads in each of those polygons. So again, those kind of operations are called spatial joints, and Earth Engine, again, they are implemented as joints. We'll learn using this example of counting how many trees fall in each neighborhood. Okay, so let's switch to our code. We've been working on this code, which we are working towards F5.3b checkpoint. I'm going to comment out the stuff that we have built so far, and we'll start with this. So we're going to add two vector layers here. This is the SF neighborhood, which is the polygons representing different neighborhoods in San Francisco, and SF trees. This is a large point layer, which is all the trees in San Francisco. Amazing data set, again, publicly available, and you can see where every tree is in San Francisco. So let's just visualize the neighborhoods. So we can say, let me just add it to the map just to show you what this looks like. So if these neighborhoods. So if I add it to the map, you will see that this is just polygons covering the city of San Francisco in each of these neighborhoods. Let's visualize this in a little better way since we're learning about vector visualization. So we're going to learn about this function called paint. So let's say let's say we want to style it so that we just have the outline and no fill. And this is not possible with the default visualization. And you can specify a color and it'll be a 50% opacity fill that you get. If you want only outline, you need to use the paint function. So again, paint function works by you first create an empty image. So we'll take this e.image, and since we want to just have a small number, we can use byte, which is an 8-bit pixel value. So you can store values from 0 to 255, which is enough for our case. So we'll take this image and we'll paint it. So these are the different options for painting. So which feature collection you want to paint on this empty image? Let's say I want to paint this SF neighborhood. Color. Here we'll, instead of giving a value of a property, we'll just give a static value. So all the pixels should get color 1. If you don't give the width value and just leave it like this will give you an image where every pixel value is 1. But if you give the width parameter to a non-zero number, it'll only render the outlines. And this is in the documentation of the paint function. See the paint function, it says if you give a non-zero width, will only render the edges, not the fills. So now you'll get this width 3 outlines with no fill of the color 1. So this is the output of this. And we can visualize this. We'll say map.add layer. We'll take this outlines layer. This is an image. So we can do all the image visualization. We can clip it. And we can, you can see the color value will be 1. There'll be only value 1 in the whole image. And we'll say wherever there's 1, we'll just keep a palette blue. Okay. And just say this is your style parameters for images. All right. Let's run this. So this is going to take our polygons, run this paint function, and it's going to paint only the edges. And you can see now we have these polygons rendered with only the edges and no fills. A question often comes up is, what if I want to fill this with a different color? How do I fill this with, say, yellow and outline? Well, you can paint it multiple times. It's also, if you look at the docs for feature collection visualization, they have an example where you just paint it twice. So you paint it once with the edges, paint it again with the fill. So actually you paint it with the fill first and then paint it with the edges. So just run two paint functions and you'll get a different color fill and outline. So again, you can use this multiple times. So this is a neighborhood that we visualize. Let's visualize our points data. So we have our trees data. So we'll have our SF trees. And this time we're going to use the style function. So we'll take our trees. This is the point data. We're going to call this function called style. Remember in the previous section, we had created a new property called style for every feature, and we had used to say style it according to this property and all the parameters containing that. If you want to apply the same style to all the features, we can just use style function, and which will give us this option. So we can specify any of those options for us to use. So it's a color, what color we want to specify, point size, how big should be the point, let's say 2, point shape. There are many different shapes available. Let's just see what are the options that are available to us. And you can see point shape. We have circle, square, diamond, cross, etc. And this all come from matplotlib. So if you use matplotlib in Python, these are the same options. So this is kind of based on the same language options that you have. So let's give, say, point shape would be triangle. Width would be the width of the outline. And again, you can give different parameters, different things. And now we have the style parameters. So let's just visualize the style data. And I'm going to zoom in a little more so you can see those points. So you can now see these points rendered as a green triangle. And you have the neighborhood boundaries in blue. And again, you can change to different shapes of this. If I say diamond, you get diamond style pin, right? So you have different marker options that are available to you. And again, people use this a lot to say, if you have some ground control points for your supervised classification, you want to visualize each class with a different color or different symbol, just to make the visual identification easy. You can use this as well. Okay. So now let's do a joint. So our goal for this exercise is we want to count how many trees are there within each of these polygons. Okay, so we have two collections, which we have the neighborhoods, we have the trees, and we want to count number of trees within each neighborhood. So we'll have to do a join. Okay. So first define a filter. So we'll use intersect filter. So every tree that intersects each neighborhood polygon, we want to select that. So we'll do e-filter intersects, and we'll specify these values. So that field will be .geo, geometry, intersect with the right field. From the secondary layer, we'll want to also intersect the geometry, and we'll just give a non-zero max error. And again, all the parameter values are always, distance is always in meters. So we'll give 1 meter as the error that we can tolerate when doing this filter. And we'll define a join type. So we'll do a join called save all join. So the save all join has different things. So what the save all join does is when we apply the join, so we'll take a polygon, and we'll join it with all the trees, and it'll find all the features and say, I found 1,000 trees in this neighborhood. I found 1,000 features from the secondary collection. What should I do with it? And you can specify a key, say, create a new property named whatever trees here, and store all of them inside the property. So you have a polygon, you'll get each polygon with a new property called trees, which will store all the matching features inside of it. Okay, and there are some of the parameters we can skip for now. And so this is our join. And now we'll apply the join. So we'll say, we'll take our save all join, dot apply, and okay, we need to give the primary, secondary, and the condition. So we'll say the primary condition, primary collection is the SF neighborhoods. The secondary collection is the SF trees. And the condition is the intersect vector. Yeah. Let me just print the first feature from the output just to show you what happened. And this kind of operation is very, very different. So if you've never done joins before in Earth Engine, if you just say, I know how to do this in a GIS, this workflow is very different. It's unique to Earth Engine. It's just how the Earth Engine team has chosen to implement it. It works, but it's very different. So if you say, why do I have to go through all these hoops to do a spatial join? Because that's how it's implemented. So we took, defined a filter, we took our neighborhoods, we joined it with the SF trees based on all the points that intersect with this polygon. And we end up with a new property called trees. You can see there's a neighborhood was already there. We get a new property called trees, which has a list of all the matching features which intersected with it. You can see there are 13,000 features that intersect, and you get them as a new property. Right? So you get, and you can do something with it if you want. So again, this is very different, but again, this is how the save all join filters work. You have filters like save first. So instead of you have multiple features, you say, I just want the first one. Sometimes that may be appropriate. There's also save best. So you can say save best means select the feature which is the nearest. You can specify measure on how do you want to measure what is the best one, and or minimum, maximum. You can use that to find the best feature for your particular purpose. But if you want all features, the save all join will save all the features into a new property. So we have this join collection. Now I don't need all this list of 13,000 trees inside my property. I just want to count. So let's just post-process this result and say we'll just count, have all the features. So we'll take, we'll create a new variable, and we'll take this joint collection, we'll map a function. So I'm just going to map a function. Each function will get one feature. And once we have the features, we'll just say, I just want the count of trees inside it. So first we'll extract the trees. So it's a f.get trees, and this will get you this list, right? So the property trees will contain the list of matching features. So the trees within is a list of all the features that is intersecting this particular neighborhood. And we'll just say total trees is within dot size. So dot size will tell you how many features are contained in a list. So we'll just get this dot size here. And because we got it out of a feature, we don't know what is the type of this. We'll explicitly cast this to a feature collection. And we can call size on it. So now we have the total trees. We'll just return this particular feature and say this is the total trees, is this number total trees. Let's print the first element and see the result. And this is what I mean by post-processing. Generally, when you do a join in Earth Engine, you typically have to map another function to kind of extract the useful data that resulted from the join. So you can see now we had this two properties, the neighborhood and the trees. And sorry, I need to print this one. So we had this neighborhood and then list of all the matching trees. So, I just need to pass this also. Okay. So now we have three objects. We can see we had our neighborhood, we had a list of trees, but also a new property called total trees with just the number of trees. And that's what we want. We don't want this in our output. So now we have each polygon of neighborhood with the total number of trees that intersected that particular polygon. And we have our results. So now what we want to do is, again, this kind of operations can be very large. If I just print it, it may time out. So I just want to export the results. So I'll just say export this to my drive. So export result to drive and control space to autocomplete. So we'll say I want to export this SF neighborhoods results. Say tree count. I like my exports to go into this folder called Earth Engine, my drive, so that my drive is not cluttered. I will name the file as tree count. The format, we just want a CSV. So we don't care about the geometry. We just want the neighborhood and the tree count of that. Here's a key part, but if you run the export without any additional parameters, you'll get an error saying that I can't export a list of features in a CSV file. And this kind of node format supports property, an attribute with a list of features, right? So this is an Earth Engine specific thing, so we don't want to export this. So the selectors parameters is key here, which is out of all the properties, which subset of properties you want to export. And we'll say, I just want the neighborhood and the total trees. So these are the two properties I want, and don't export anything else. And now once I have this, I can run my script. It'll have an export task. And once I run this, I'll get a CSV file in the drive. I did run this export just before we started the session. So let me show you what that output of the result looks like. So you can see there's a file called treecount.csv in my drive. And you can see now I have this nice CSV with the neighborhood and the number of trees that are within each neighborhood. And this was created by doing the join with the two different layers. And you can use the CSV in your analysis. Now you should have the full script in your checkpoint F53B in your code repository, and you will have the complete script there. Thank you. I want to also show an additional resource. If you liked this vector operations, if you're using Earth Engine for vector analysis, I gave a talk a few years back at an Earth Engine summit, and I've linked to the slide here. And this will contain a lot more examples. My favorite one is geodesic buffers. So if you want to compute geodesic buffers, Earth Engine can compute geodesic buffers, very interesting use cases of those. So do check out those slides that I've linked here. And there are more vector examples that you can use and apply in your work. So hope you learned something new and continue exploring Earth Engine. Thank you.